Welcome back everyone, and today I'd like to continue our discussion on acids and bases. And as I mentioned in the previous video, when I said what happens if there are no pK values given to us, well, now that's what we're going to talk about in this video. And what happens is, to predict the acidity when we're not given quantitative data, we have to look at these four factors, which I'm going to mention. And this is our qualitative perspective. So the first factor that I want to mention is which atom bears the charge. And I know that sounds kind of weird, so I'm kind of just going to explain what it means. So the first factor revolves around the fact of deprotonating. So recall that deprotonating is losing that hydrogen essentially. And basically what it says is that the atom with the more negative charge on it after deprotonation, the one that's more electronegative out of the two, is the one that's going to be more acidic. And I know that doesn't quite make sense, so I'm going to hopefully show you this example and hopefully it makes sense. So if I wanted to compare the acidity of these two right over here, if I were to deprotonate, I would get a negative, I'd get a lone pair and a negative formal charge on the carbon. And if I did the same thing here, I would have the exact same thing except on the oxygen. And notice that the oxygen is more electronegative than this carbon. And since the oxygen is more electronegative than the carbon, this has to be more acidic. That's essentially what I was trying to explain in the beginning. But there is a slight modification to this rule. So, for example, if I looked at these two and I did my deprotonation, I'd have the OH and the SH. And what you would say is, well, since electronegativity increases as we're going up a column, the oxygen is more electronegative than the sulfur, and therefore the oxygen wins and is more acidic. But that would be wrong. And why it would be wrong is because the slight modification to this rule is when you're comparing the negative charge on two atoms that are in the same column. So note these are in the same row, the carbon and the oxygen, but now the oxygen and the sulfur in the same column. You look at the size of the atom. And since the sulfur atom has more electrons and protons, it's larger and can better stabilize that negative charge. So therefore, that's why this will be more acidic than this. So once again, if you're looking at the two atoms after deprotonation that are in the same row, you look at electronegativity, the one that's more electronegative, more acidic. But when you're looking at two atoms for the negative charge that are in the same column, you look at the size. And since this has a greater size than the oxygen atom, this is more acidic. And a good helpful tip is, as we're going down a column, our size is always increasing. So that was the first factor. And now we're going to move on to our second factor, which is resonance. And basically, all that said here is, if there's resonance in one of these structures, then that one's more acidic. So if I first deprotonate, so that's always my first step, I get this. And if I deprotonate over here, what I get is this. But as you can recall, this structure has resonance, but this doesn't. And exactly how this has resonance, as I'm going to review again, is over here. So remember, if we use our proper resonance notation, so right, like that. So since this has resonance and this doesn't, this is more electronegative. That's actually it for resonance. Simple as that. And now we move on to our third factor, induction. So what if we had an example like this? So let's look at our steps from the very beginning and see what we can do to this. So the first step is always going to be deprotonation. So let's deprotonate both of them. So, and if I deprotonate this one, and notice how in the last example this did have resonance. I'm not going to draw the arrows, but there would be one there and there. But if I look over here as well, I have resonance here as well, the exact same thing. And if I notice, the negative charge is on the exact same atom, so neither of the first two factors work. So now what I want to focus our attention towards are these chlorines in the second structure. Notice from the notation we use for induction, since the chlorines are more electronegative, they are the partial negative, partial positive, partial negative, partial negative, and our arrow notation shows them going outwards like this. And since we have this inductive effect, that helps stabilize the charge, the negative charge. So that's why this will be more electronegative than this, because of the inductive effects in this case. And notice if I added even more chlorines, that would be an even more acidic compound. So for example, if I had a compound with 3 chlorines and then I had another compound with 4, the one with 4 would win. That's only being provided that both the structures have resonance and have the negative charge on the exact same atom. But that's induction. So if you kind of see chlorines, fluorines, kind of halogens around, that's a pretty good indication that you have induction. And now our last factor, orbitals. So what if we had an example like this, and I asked you which hydrogen, so which proton is more acidic, this one or this one? Well, your first step would always be depronation. And notice how they're in this structure, they're both on the carbon. There is no resonance in this case, and there's no halogen. What do we do then? And now the key thing about orbitals is you always look at something called hybridization. And I did cover this in my review section, so you should check that out if you haven't. And now primarily what we're going to do is we're going to look at this, and we're going to look at that. So this is basically just a double bonded, this carbon has a double bond, and then it has a lone pair and another probably a hydrogen. So we know that this is sp squared hybridized. And if I looked at this carbon has a triple bond with just lone pair tacton, we know this is sp hybridized. Now, how does that help us? Well, the main idea is basically sp hybridized orbitals are closest to the nucleus, so they can better stabilize that negative charge. In the sp cubed or hybridization, the orbitals are further away from the nucleus, so the charges and the negative charge isn't as well stabilized. So in general, from what we know based off of this fact, the sp hybridized will be always the most acidic. Then second is sp squared, and then followed by sp cubed. So this would be the least acidic. And a good typical indication of hybridizations when you have typically double, and especially when you have triple bonds. So yeah, not always necessarily a double bond indicates hybridization, but a triple bond is a pretty good key. But always make sure for double bonds you check. In this case, there is no resonance, so that's why we had to look at orbitals. So yeah, so in this case, since this one is sp hybridized and this one is sp squared hybridized, we know that this would be more acidic. So those are the 4 factors that we generally use in our quantitative perspective to determine acidity. And now what I'd like to talk about is a brief exception to the rule. So this is generally, I think, there's a few exceptions to this rule, but generally this is the most important one. So actually, before I even talk about the exception, ranking of the factors is more important. Now, how do we know which factor is more important than the other? And the method is, the way I presented them is the order of importance. So therefore, the first factor has precedence over the second factor, which has precedence over the third factor, which has precedence over the fourth factor, in that exact order. But now, in this exception, which we're going to talk about, this is the only exception I'm going to talk about because this is typically usually the most common one, we're going to talk about what happens. So if I deprotonate even one of them, hydrogens, I'll get the negative charge there. And what will happen here is I'll have negative charge there. So if you look at both of them, you know that nitrogen is more electronegative than the carbon, so this would win by factor 1. But if you also look at factor 4, this would win based off of factor 4. So based off of factor 4, again, this would be more acidic, but based off factor 1, this would be more acidic. And what I just said was, well, since factor 1 takes precedence over all the factors, therefore I don't really need to consider factor 4, and therefore this should be more acidic. And in a general sense, yes, you are right, that is exactly true, but this is where the exception comes in. Whenever you're comparing a carbon and a nitrogen, so the negative charge on a carbon and nitrogen, the carbon always wins. I'm not exactly 100% sure as to why, but most textbooks have it this way. So once again, I'm going to repeat that. This would win by factor 1. this would win by factor 4. But since we know that factor 1 takes precedence over factor 4, we would say this is more acidic. But now the exception comes in, where if we have a negative charge on a carbon and nitrogen specifically, even though the nitrogen is more electronegative, since they're in the same row, the carbon wins. So therefore, this is more acidic. So that was the only quite a small exception I wanted to kind of talk about. And now I'd like to move on to some practice problems. And I guess we'll begin over here. So what I encourage you guys to do is pause the video and work on the examples, and then unpause the video and see how you did. So I hope you do that now. And so I hope you guys pause the video and try the examples out. So now let's work on them together. So for each of the pair of compounds below, identify the more acidic compounds. So if I look at these two and I deprotonate each of them, I get the negative charge on the oxygen, and here I get the negative charge on the sulfur. And since these are in the same column, based off of factor 1, we look at size. And since sulfur has a greater size than oxygen, this is more acidic. Now if we go down and look at the next example, I'm going to do the exact same thing, so I'll kind of draw them both over here. So if I deprotonate the first structure, get the negative charge on the oxygen, and I got a bunch of chlorine sticking around. And if I do the exact same thing to now this second structure, and now I look at them, well, the negative charge is on the same atom, so factor 1 doesn't help me. And since we know from resonance structures, these both have resonance in their ring, that doesn't help us. But now we notice that these have halogens, and we know that this is a good indication of an inductive effect. Since this is more electronegative than the carbon, the partial negatives over here and the partial positives over here, and we move our arrows outwards in this direction. And since this has inductive effects and this doesn't, we know that this is more acidic. So now we can move on to this example. So now be careful about this example. So if I deprotonate this one, what do I get? I get a negative charge here. And if I deprotonate this one over here, what I get is a negative charge over here. Now, if you recall, these don't have resonance or any inductive effects. This negative charge on the nitrogen is more electronegative than the negative charge on the carbon. So this wins by factor 1. But as you can see, this wins by factor 4. But we know, well, this wins by factor 4. First, I should explain why, is because this is sp cubed hybridized and this is not. But we know that factor 1 takes precedence over factor 4. But remember that exception. Whenever you're comparing a negative charge on a nitrogen and carbon, even though the nitrogen is more electronegative, the carbon wins. So therefore, this is more acidic. And it is the exception. So, yeah. And now, if we look at this last example over here, if I deprotonate, I get the negative charge on the oxygen. If I deprotonate this one as well, I get the negative charge on the oxygen as well. So factor 1 doesn't help us, and there's no other orbitals or inductive effects to consider. So the other second factor we consider is resonance. Well, I know that this structure over here does have resonance. Now I'm not going to draw the arrows, but if I wanted to, actually I'll just draw them here. So guess this is our resonance structure. But this doesn't have resonance. Since this doesn't have resonance and this does, we know this has to be more acidic due to resonance. So there's that one. And now let's do some other types of examples. So each compound identify the more acidic proton. So now let's see which proton is more acidic. So how I would do this example is I would just deprotonate both the protons at once. So you have the negative formal charge on the oxygen here, and over here you got that negative charge on the oxygen as well. So since the negative charge is on the same atom, factor 1 doesn't help us. Now, what I notice is, in this case, there is resonance. So I'll just kind of show it, I guess. So we can move these arrows to show resonance there. But in this case, this has an inductive effect because there's no resonance here, but this does have those chlorines, so it does have that inductive effect, so the partial negative and the partial positive. Now, factor 2 takes precedence over factor 1, so therefore this side takes precedence over this side, which means that this hydrogen has to be more acidic. So now we can move on to the next one. And now over here, if I depronate, I notice that I have a negative charge on the oxygen and one on the sulfur, and since these are in the same column, we don't look at electronegativity but at the size. We know the sulfur has a greater size, so therefore this, well, specifically this hydrogen, has to be more acidic. And now I'd like to talk about this last example, and I encourage you guys to pause the video for this specific example and try it out on your own. This is probably the most trickiest one, and if you can figure this one out without any help, you've pretty much mastered this topic. So I hope you go and try this right now, and let's see how you did. So I hope you guys tried the example out now, and I'd like to now continue. So now we're going to understand why this example, I would say, is the hardest example. Now if we depronate, so I guess it's beneficial if we just depronate both of them at once, I guess. So that's that. Now factor 1 doesn't help us because this is both on the carbons. There's no inductive effects and no orbitals to consider, so our factor 2 is going to help us, resonance. And I hope you guys have realized that both this and this do indeed have resonance. And here I'll even show you. So well, let's start with for the left hydrogen. So I'll even show that right now. So if for the left hydrogen, let's just assume that that hydrogen is not deprotonated, it's just left as it is. We have that resonance over there. And now you're not done yet, because if you've properly looked at this structure, you'll notice there indeed is another resonance structure that you can do. What I can do is I can move this back here, I can move this over, and since we don't want to break the octet, we move that pair over. So now I have this. And now if I do the same thing for the right hydrogen, so if we have the right hydrogen now, so we'll just assume that the left hydrogen now is remain as it is and it's not deprotonated. I can move this over here and this over here. And this will only have one resonance structure. And that's that. So now, if you look at this, what you might be thinking of saying is, well, since the left hydrogen has two resonance structures, well, I mean more than one resonance structure, so 1, 2, 3, then therefore this has to be more acidic than this because this only has two. But I want to say this, and I don't want to stress this enough, that's not a valid reasoning. We don't care about how many resonance structures this has and this has. What we do care about is over what atoms the resonance is stabilized. So if I notice over here in this case, I have a resonance stabilized over an oxygen atom over here, so it's over a carbon and oxygen atom. But if I look over here, it's also stabilized by another oxygen atom over here and another carbon atom, so a carbon atom and an oxygen atom. But I don't really care about these carbon atoms. What I want to focus my attention on is the fact that it's resonance stabilized over an oxygen atom, which is electronegative, and another oxygen atom over here where it's electronegative. But if you look in this case, it's only stabilized over one oxygen atom. So over two oxygen atoms, resonance stabilized. And in this case, it's only over one oxygen atom, which is right over there. So this is more acidic than this, mainly because it's resonance stabilized over two oxygen atoms and not one. So once again, it doesn't matter if this has more resonance structures than this. The only thing we care about is that this is resonance stabilized over two oxygen atoms, while this is only resonance stabilized by one oxygen atom. So that's why that is more acidic than this. And well, those are all the examples I wanted to cover today. And in the next video, I'm going to wrap up acids and bases and then move on to nomenclature of alkanes and talk about what they are and everything else. So if you have any questions, comments, concerns, you can email me or comment down below and I'll get back to you as soon as I can. And thanks for watching.